In this video, we're going to be working CalBC homework 3.2, and we're going to be finding, intervals on which a function is concave up and concave down, inflection points, probably some more max min questions, just more analysis of a function by looking at its first two derivatives. All right, so the first questions are asking us to find points of inflection and determine intervals of concavity. So what we want to do is make just like a full-blown sign chart of f double prime. For both of these things, like concavity and points of inflection, we want to be thinking about the sign of the second derivative. So I'm going to start by taking f prime. It's a little bit thicker than I need. So I'm going to use the power rule, multiply the negative 2 by 3, subtract 1 from the power, and then f double prime would be negative 12x. Okay, now you can make a sign chart or you can sketch the graph. Either way, I think I'll probably be doing some of both on this video. But either way, this is going to equal 0 at x equals 0, and you're going to end up with this if you make a sign chart, or that if you sketch the graph. Obviously I should have sketched and then labeled the 0 after that, but either way you're getting the same information. We're going to see a sign change at x equals 0, so that'll be an inflection point at x equals 0. With concave up from negative infinity to 0 and concave down from 0 to positive infinity. All right, for number 2, we're going to do the exact same thing, and we're going to say first f prime is 3x squared minus 4 over 6x to the third, and I'm just going to have faith when I take the second derivative. Yeah, that'll work out better. F double prime is going to be 6x minus 12 over 6 is 2x squared. Okay, now I can factor this. Factor out a 2x from both terms. Okay. See, okay, well, this is a downward-facing parabola, and it's got two distinct zeros, so probably look a little bit like that. The zeros are at x equals 0 and x equals 3. Or you could make a sign chart and make your determination that on the interval 0 to 3, f double prime of x is positive. On the interval 3 to infinity and negative infinity to 0, f double prime is negative. And you end up with that type of sign chart, seeing points of inflection like sign changes in the second derivative at x equals 0 and x equals 3. Concave up happened from 0 to 3. And concave down was negative infinity up to 0 and also 3 to infinity. All right, number 3 is another fourth degree polynomial, so I kind of expect this to go about the same. I'm going to say the first derivative is 4x to the 3 minus 6x to the 2 minus 72x to the 1. Oh, okay, but I see where this is going. G double prime is going to equal 12x to the 2 minus 12x to the 1 minus 72, which if I factor 12 out of that will, I think, be pretty factor. Yeah. Yeah, now, let's say, wait, this is going to be a second degree polynomial with a positive leading coefficient. I didn't like that one. Didn't like that one either. That'll have to do. And we're seeing zeros at x equals a negative 1 and x equals positive 2. And so our points of inflection is going to be where the sign changes. Now, if you done a sign chart, you should have gotten this. Okay, the points of inflection would be where the sign changed, and that would be x equals negative 1 and x equals positive 2. Concave up, that's going to be x is less than -1 or x greater than 2. Concave down would be the interval between -1 and 2. And of course, those intervals would be just as good, just like in the last lesson. We don't care about open versus closed, if we include the endpoints or not. That's just like not anything we're going to get into here. Okay, now number 4, that's got a little bit more going on. I'm going to, kind of paste in this for later, but I'm going to need to take my first two derivatives. This first one, this is chain rule. On the outside, I've got the cube, and on the inside, I've got the x squared minus 1. So outside prime times inside prime, 2x minus 0. I'm going to leave the inside of the parentheses the same. And now I think I would definitely be smart to rewrite this as 6x multiplied by x squared minus 1 squared. Okay. Oh no. All right, not totally sure what happened there. Okay, I feel like I've just been talking through the algebra, and so g prime was, okay, we got it using the chain rule. To take g double prime, I'm going to need to use the product rule, because I've got the 6x and the x squared minus 1 squared. When I take the derivative of x squared minus 1 squared, just like when I took the derivative of that thing cubed, I'm going to need to be careful with the chain rule, but we've got this. So first, I'm going to say, all right, take the derivative of 6x, keep it easy on yourself, and leave the x squared minus 1 squared right there. Then we're going to add, leaving the 6x the same, taking the derivative of x squared minus 1 squared. Okay, on the outside I've got the squared, and on the inside x minus 1. So. All right, and now I can tell this, I just am going to need to factor this. There's not really any sense in simplifying it when I'm just about to go factor it also. And there's going to be some more factoring. This one's going to be pretty intensive. So I'm going to factor the 6. I can see that's in both terms. I'm factoring really on this addition right there. Okay. In both of them, I'm seeing the 6 and 1 copy of x squared minus 1. Okay, and then I would be left with one more copy of x squared minus 1, then plus, that's the same plus that it was in the other highlighted plus. And the second term, I factored the 6, so I'm going to have two 2's, two x's. But I did factor out the x squared minus 1. Okay. Okay, and now I can keep going on this. 6 times x plus 1 and x minus 1. And then the thing in squared brackets is going to be 5x squared minus 1. All right, now at this point, I'm pretty much done factoring, maybe tired of factoring. Yeah, I'm sure I could go farther. But I'm just going to think about, I've got the first 3 factors, and then that 5x squared minus 1, I can figure out where that's equal to 0. I'm just going to go off to the side and say, okay, where does 5x squared minus 1 equal 0? Only 1 power of x, I could solve for it directly. X squared equals 1/5. That's going to be square root of a fifth and negative square root of a fifth. Okay, well, the graph of this thing is going to be a 4th degree polynomial with a positive leading coefficient. I could sketch that. So there it is. And then I could figure out the points of inflection. It's going to be all of them. So it's going to be, let's see, x equaling -1, negative square root of a fifth, which is the same as 1 over the square root of 5, positive 1 over the square root of 5, and positive 1. Okay, concave up would be this one was intensive. I'm not sure I love this question that much anymore. I would include it if I was making the homework anew, but it'll be all right. All right, there we go. We found the intervals of concave up and concave downness and found the points of inflection. And I mean, it was really good chain rule product rule. I really did like that. The factoring was interesting, but that's definitely more difficult than anything we're going to see on a quiz or test in this class. Okay, next, what do we have? When does the graph of f have a point of inflection? When is the graph of f concave up? But they're going to start us with f prime. That's nice. One less derivative to take. So I'm going to say, all right, start by taking a derivative. Interesting. That's a second time this algebra has come up. The difference of two squares, but the second square isn't quite perfect. You can factor like this if you want. That works. Now, I will say, okay, does it have a point of inflection? X equals positive square root of 3 and x equals a negative square root of 3. Oh, I froze up on that. All right, I might, remark that those are the sign changes of f double prime, which is why we're going to be having points of inflection. And I know that, pardon me, I kind of skipped over that fact. I know that because, it's a second degree polynomial with a positive leading coefficient, two distinct zeros, those are both sign changes, or I could make a sign chart and see this is going positive, negative, positive. Okay, then as far as concave up, that would be where the graph of f double prime is positive. So as for where the graph is concave up, I would say that's going to be negative infinity up to negative square root of 3, also square root of 3 to infinity. Okay, and I would say because f double prime is greater than 0. Now we're going to get f double prime factored and asked about a point of inflection. So this is really just about the sign chart or the sketch of the graph. So I'll start with the sign chart. 0, 3, and negative 4. So I got those. I'm thinking, you could start with, I'm going to start with 1. It's between 0 and 3. I'm going to plug in 1 squared, 1 minus 3, 1 plus 4 to the fourth. That's going to be a negative number. Okay, now at x equals 3, that's a single root, so I will see a sign change. X equals 0 is a double root. I won't see a sign change. X equals negative 4, a quadruple root, even multiplicities, no sign change. I could see it like that, or I could go over here and say this is a 4th, 5th, 6th, 7th degree polynomial with what's going to be a leading coefficient 1. Okay, so it's going to come from below. It's going to go up. It's going to have its first 0 at x equals negative 4. It'll be a quadruple root. So I'm going to say, all right, it's going to bounce. Didn't love that. That was even worse. All right, that'll have to do. It's going to bounce, and then at x equals 0, it's going to bounce again. And it doesn't have to be perfect. And then at x equals 3, we're going to pass through confidently. Yeah, the end behavior works, makes sense. And so if we're saying concave down, point of inflection, that was going to be x equals 3 only. Now, if that was just the question, we could have determined that based on the multiplicity of x minus 3 and the multiplicities of x squared and x plus 4 to the 4. But, thinking about concave down, we're going to be interested in where is this negative or less than or equal to 0, right? We don't really care. And so I'm going to say concave down would be when x is less than 3. Maybe I'd be wiser to say less than or equal to. But it really, like I'm saying, like I've said all along, it really, really does not matter. All right, now moving on to the next page, we've got some graphs. It looks like for for now, it's going to be mostly the graph of f prime, and it's going to turn into the graph of f double prime, and we're going to be asking about points of inflection, concave up, concave down. All right. Now, point of inflection, that's going to be where concavity changes. And if we're looking at the picture of the graph of f prime, the concavity of f is going to be, is f prime increasing or decreasing? So the inflections of f are going to be at the extrema of f prime. So I'm going to say, all right, that's going to be here at x equals -1 and x equals 1. And my reason would be f prime has local extrema. A reason always has to be centered around the information that we're given, right? So if we're given the graph of f prime, we have to give our reason in terms of f prime. We could say f prime changes from increasing to decreasing or vice versa. We could say the sign of the slope of f prime changes. That's kind of a lot to write though, and saying f prime has local extrema, that's kind of got a nice little ring to it. All right, concave up, that's going to be where f prime is increasing. And f prime is increasing when x is less than -1, and also when x is greater than 1. F prime is decreasing between -1 and 1, and that'll be where the graph of f is concave down. All right, same idea with the next one. We're looking at a picture of the graph of f prime, so the inflection points on f will be the extrema of f prime. And I'll have these right here. I'll say, all right, x equals -2, x equals 0, and x equals +2. And my reason would be f prime has local extrema. Okay, you can't quite see that, but okay, you see what I would say. Okay, concave up. The graph of f will be concave up when f prime is increasing. So that would be on the interval -2 to 0. And also on the interval 2 to infinity. All right, and then concave down, f prime is decreasing. I should probably say f prime is increasing. F prime is decreasing from -infinity to -2. Also 0 to 2. All right, there we go. Oh, okay, this one's weird. We've got a very discontinuous first derivative, and so we'll say, all right, the inflection points are still going to be the extrema. Okay, local maximum, local minimum. I would not count x equals 1 as a local maximum or a local minimum. It's kind of both. And if you think about it, f prime goes from decreasing to decreasing. So we're not going to see a change in concavity on f because that just means regular f goes from concave down to concave down. That would not be a change in concavity. We are going to have something going on there. Probably, I would imagine some sort of discontinuity, maybe just a sharp corner, but who knows? Who could say? We can't say from looking at this picture. All right, our inflection points are going to be the extrema of the graph of f prime. When there's only one, I could say f prime has a minimum at x equals 2. And otherwise, we just, okay, f prime is decreasing from -infinity to positive 1, and then from positive 1 to positive 2. And if you want to say, okay, I'm just going to say that x is less than 2, because f prime is decreasing that whole time. Now, if you want to exclude x equals 1, that's what I was saying, that would be fine. I would totally understand if you wanted to do that, why you would feel that way. But I'm going to just write x is less than 2 because we would not really even be able to see that on the graph of the original function f, besides maybe there being a sharp corner. Okay, so concave up, that's going to be where f prime is increasing. And that happens when x is greater than 2. Okay. Now, when we shift over here to the graph of f double prime, this is a different consideration. For a point of inflection, we are interested in the sign changes of f double prime. Okay, so I'm going to say, all right, well, where's the sign change? That would be here and there. That's at positive 2 and negative 3. So x equals negative 3 and x equals 2, and my reason would be f double prime changed signs. And concave up is when f double prime is positive. Okay, well, f double prime, looking at the picture of it, it's above the x-axis between negative 3 and 2. I can see that f double prime of x is greater than 0. And then when x is less than negative 3, or also when x is greater than positive 2, f double prime is negative, the regular f of x, its graph is concave down. All right, here's another one. Very similar. We're looking at a picture of the graph of f double prime. The points of inflection will be the sign changes. So negative 2, 0, and 2. My reason is f double prime changes sign. Okay, then for concave up, f double prime is greater than 0 on the interval negative 2 to 0. Also 2 to infinity. And concave down, f double prime is negative from negative infinity to negative 2, and also from 0 to positive 2. And then here's f of x, and you probably won't, this is more of a pre-calculus level question, and you won't see this probably again, but, just to review, it's probably good to go first. By inflection, okay, that's where the attitude changes. I can see that if anything, it's going to be right there at x equals 1. I don't know how to say why that's an inflection besides it looks like one on the graph, which is not a very good reason. Concave up, it does appear like that's x less than 1, and concave down, x greater than 1. I think I might. If I remade this homework, I could do without that one. All right, number 13 is another algebraic problem where is f increasing and concave up. Well, increasing means I need the first derivative, concave means I need the second derivative, so I'm just going to take both of them. F prime is going to be 20x cubed minus 5x to the 4. And I'm going to need to factor these both, so I'll leave a little bit of extra room. I'll say the next derivative would be 60x to the 2 minus 20x to the 3. All right, now if I factor this one, I've got 3 powers of x and a 5 in common to both. 5x cubed times 4 minus x. Over here, I've got a 20 and 2 powers of x. And I'll multiply that by 3 minus x. All right, great. And I'm going to say, I think I need to make a sign chart at this point. On this one, I'll be interested in 0 and 4. I'm going to try to make kind of a parallel sign chart. Put 0 at the same spot, but maybe put 3 right here. Okay, now, do your sign analysis, sketch your graph, whatever it's going to take. Maybe I'll do a sign chart for f prime and start with x equals 1. That'll be in the middle. 5 times 1 times 3, that's a positive number. And then I'm seeing that x equals 4 is a single root, and so is x equals 0, so I will see sign changes. There we go. I've got a sign chart. F is going to be increasing between 0 and 4. Okay, then if I was going to make a graph of f double prime, that's going to be a third degree polynomial with a negative leading coefficient. At x equals 0, the graph is going to bounce. And at x equals 3, it's going to pass through confidently. And then if I'm interested in where f is concave up, that's where f double prime is greater than 0, or potentially equal. And that's going to be all throughout here. Okay. Now, if we're looking for where both of these are true, it's going to be right here. I would see red on top of blue, and that would be from 0 to 3. So you could, in an open interval, you could write it as, using interval notation, write however you're going to. But I think that's about all I've got to say. I might give a reason, f prime is positive and f double prime is also positive. Okay, and then when is f prime negative and increasing? Well, I've already done most of the work for that. I would say f prime is going to be negative. Let's make a new number line. Zero, 3, and 4. All right, f prime is going to be negative on, let's see, below 0 and from 4 to infinity. And then I'm going to have f prime increasing, okay, so that's f double prime is positive, from basically 3 back to infinity, or negative infinity. You could even put one of those there if you wanted, but where I'm seeing overlap is going to be where x is less than 0. I don't really have any more analysis to add besides what I've already shown on screen. Oh, okay, this next one's going to be a good one. Okay, same kind of problem. We're going to need to take the second derivative. Okay, this is a product, so we need to use the product rule. The first factor, I'm going to take the derivative of blue. That would be 2 times x plus 1 to the first, I guess times 1 for the chain rule, and then leave 2x minus 3 cubed the same. Then I'll add, leaving blue the same, taking the derivative of red. So 3 times something squared times the derivative of the inside. And the inside was 2x minus 3. And then I'm leaving the other factor the same. I'm going to need to factor this, and that's why we practiced that one time when we learned product rule. But again, the more you do this factoring, the less bad it is. So I would say if I'm looking to factor, I see the 2. Definitely see one copy of x plus 1. I'm factoring over that addition right there. And let's see, 2 powers of 2x minus 3. Okay, now if I factor that out, I'll be left with one more copy of 2x minus 3. The same plus And then, all right, I lost the 2, lost both of the 2x minus 3's and one of the x plus 1. So I'd have a 3 and an x plus 1. Now I'm going to keep working on that and say, okay, 2x minus 3 plus 3x plus 3. Oh, that's just going to be 5x. And I do remember this problem from a couple weeks ago. So 10x, I'm just going to put the 2 and the 5x together. X plus 1, 2x minus 3 squared. That's the second derivative. All right, now I'm going to make a sign chart for f prime. Or maybe a sketch of the graph. This is a fifth degree polynomial with a positive leading coefficient. I don't know what that looks like. First root would be at -1. That's a double root, a triple root. Remember, it's kind of hesitant. What that actually means is that there has to be a point of inflection there. But I would let you think about why that's true, or come talk to me about it, some morning before school. Why one of those bends at a triple root must be a point of inflection. Okay, anyway, so I determined this is -1, and this is going to be 1.5. Sketched f prime, maybe I'll make a sign chart for f double prime. So -1, 0, and 1.5. Oh, I can just probably use the same scale. Let's see, all right. Okay, x equals 1 would be an option. Plug that in. Okay, positive, positive, -1 squared. Okay, that's all positive, so I have that there. Okay, 2x minus 3 is a double root, so I'm not going to see a sign change here on f double prime. And then x equals 0, that was a single root, so it's x plus 1. All right, and then thinking about the degree, second, third, fourth degree polynomial, positive leading coefficient. Yeah, that end behavior looks right. Okay, this makes sense to me. All right, so if we're thinking about f being increasing, okay, that's where f prime is greater than 0. Increasing and concave down? Never. So I would say f prime greater than 0 and f double prime less than 0, never. That's a major letdown after all that factoring, but okay, whereas f prime less than 0 and f double prime less than 0, that'd be, okay, where both of them are showing negative, that's going to be -1 to 0. Okay. Where's f increasing and concave down? Okay, well, f is going to be increasing when f prime is positive. And the graph of f is going to be concave down when f prime is decreasing. Okay, so where we've got, well, actually, I don't really like the way I drew that. I should probably say like that. Okay, and where we're having overlap of both blue and red is going to be, right here where x is less than -3. Also here between x equals 0 and x equals 1. Then the graph of f is shown below. Determine if these are positive, negative, or 0. I've definitely seen multiple choice questions like this, lots of different ones where they have you rank these in order from least to greatest. Okay, but we can just do what they're saying. F of 3, f prime of 3, f double prime of 3. All right. F of 3, that's equal to 0. Right? We're seeing the graph of f. F prime is going to be negative because f is decreasing, and f double prime would be positive because the graph of f is concave up. Right. The graph of, I think I meant to call that f, is shown below. Order f of 3, f prime of 3, and f double prime of 3 from least to greatest. Okay, there you go. So I'm just going to go ahead and say, okay, f of 3 equals 0. f prime of 3 equals a positive number, and f double prime of 3 is going to be a negative number because the graph of f is concave down. And so ordering them from least to greatest, the negative one would be the least. F of 3 was 0, and f prime of 3 is going to be greater than 0. Right. Give an interval over which the derivative is positive and the second derivative is negative. Okay, derivative is positive means, okay, the graph is going up, and second derivative means the graph is angry, so we went uphill angrily. That's going to be right here. Okay, the rest of the points are either going downhill or going uphill. Wait, this is also going uphill angrily. I don't know why I was trying to miss that. I know that I've seen that wrong answer on student responses before. I guess I can empathize with that now. Okay, so yeah, nobody said anything about f being positive, so that'll work. Then I'm going to say, okay, that's from x equal, really, all x less than negative 1. Ah, some particle motion. Great. Speeding up and slowing down. Wonderful. So we just need to determine, are the signs of velocity and acceleration the same or opposite? So it would probably be good for us to get velocity. So v is going to be the derivative of x. That would be 4 minus 10 sine of 5t. I need to use the chain rule. The derivative of the outside would be negative 2 sine of whatever, and then the derivative of the inside is 5, and so I multiply those, and I'm going to get the negative 10. And then the acceleration, that's the second derivative of position. And that's going to be negative 50 cosine of 5t. Speeding up or slowing down at the time where t equals pi over 6. Well, I'm going to plug in pi over 6 and get 4 minus 10 times the sine of 5 pi over 6. Okay, that wasn't my best one ever, but okay, 5 pi over 6 is almost all the way to pi, so it's not very high up. That would be a sine of half. So 4 minus 5 is less than 0. Acceleration at time pi over 6, I'd have negative 50 times the cosine of 5 pi over 6. Okay, 5 pi over 6, the cosine is going to be a negative number, so that's going to be greater than 0. I'm going to say slowing down because v of pi over 6 and v prime of pi over 6 have opposite sign. Now, the velocity is given by v equals t squared minus 5t. At t equals negative 1 is the speed of the particle increasing or decreasing. Okay, so we need velocity and acceleration. Okay, so v at t equals 1. It's going to be 1 plus 5 equals 6. And then the derivative of v just take it and 2t minus 5, so that's going to be 2 times 1 minus 5. That's negative. Am I missing something here? No. Sure about that one. So, okay, opposite signs. At t equals -1, so speed is decreasing. Now we've got the graph of a velocity, and I want the intervals on which the acceleration is positive. Well, the acceleration is going to be the slope of the tangent to the velocity. I'm going to also just be looking for places where velocity is increasing. So it looks like it must have a horizontal tangent at 1, is what they're trying to show me. Okay. Give the intervals, that would be from 1 to 4. 1 less than t less than 4. The slope of v is positive. All right. On the time interval 2 to 3, is the particle speeding up or slowing down? Explain. Well, slowing down because it's moving closer to 0. Okay, at t equals 3, the velocity is 0. But our answer needs to be in terms of calculus. Okay, I'm going to say on the interval 2 to 3, v less than 0 and v prime is greater than 0. Okay, and or you could say and v is increasing. I would say probably is probably a better way to say it. So velocity and acceleration have opposite signs. All right, that's it, right? Yep, that's all for this video. Thanks for watching.